Hello, this is a presentation of LOG-a-TEC sensor network testbed. This is the overview of the presentation. First, I will present the hardware, then I will present the software stack of the Vesna platform. In the following, I will present the LOG-a-TEC sensor network testbed and how you can access it remotely. And at the end we will go through some interesting demos to see how we can interact with our remote LOG-a-TEC sensor network testbed over the internet. In this picture we see the actual hardware of the Vesna platform. And this is how the components fit together. First we have the sensor node core board with a microcontroller, then we have the sensor node radio which has the radio, and on top we fit the sensor node expansion board which is application specific. Our sensor node core has an STM ARM Cortex M3 microcontroller, and it has a clock up to 72 megahertz and 1 megabyte of flash and 96 kilobytes of RAM. It has also non-volatile storage, and this is 128 kilobytes of fast MRAM. And we also had the possibility to use a micro SD card, and the power supply is from a battery, solar cell, or external power. The sensor node radio has a Zigbee wireless mesh Atmel module. We use this radio for the management network. This is a radio in 868 megahertz ISM band. The sensor node expansion board was developed specifically for a crew project, and the purposes of this expansion board is data acquisition, sensor interfaces, wired to wireless communications, and extra power supply. So this is basically the general description of the expansion board. But more specifically we developed the sensor node expansion board ISM TV for crew, and specifically for spectrum sensing and cognitive radio applications. This board includes a collection of radio frequency hardware, and the most important is UHF wideband energy detector receiver. Then we have the reconfigurable narrowband sub 1 gigahertz transceiver, and the reconfigurable narrowband 2.4 gigahertz transceiver, and also additional IEEE 800 to 15.4 compliant radio which operates on 868 megahertz. And all these radios are independent of the management network. So this is a more specific description of the ISM TV UHF receiver. This is based on the NXP TDA 18219 silicon tuner. It has a frequency range from 470 to 862 megahertz. The bandwidth is 8 megahertz in 1.7 megahertz step, and the dynamic range is 60 dBm. The next two radios are also meant to be used for energy detection measurements and uh, also test signal generation, interferer simulation, and experiments with packet-based protocols. So the Texas Instruments CC1101. This is a sub-gigahertz transceiver. It has a frequency range of 780 megahertz to 871 megahertz. This transceiver operates in 868 MHz ISM band, and it also covers the upper channels of the UHF band, and the maximum transmit power is 12 dBm. The next transceiver is Texas Instruments CC2500. This operates in 2.4 gigahertz ISM band, and it has a maximum transmit power of 0 dBm. On this slide, we can see the Vesna software stack. In the bottom, so we have two options: to use libopencm3 library or the STM32 firmware library, and based on these two libraries we then build the drivers, and on top of the drivers we can have the Contiki operating system or directly the application. So a few informations about LOG-a-TEC testbed. We have 51 Vesna wireless sensor nodes, mostly mounted on the street lights, some on rooftops, and more specifically we have 32 sensor nodes that operate in 2.4 gigahertz ISM band. We have 11 nodes that operate in 868 megahertz ISM band, and we have 5 sensor nodes that operates in UHF band with low gain antenna, and 3 in UHF band with high gain antenna. So there are 2 clusters in the municipality of LOG-a-TEC. First is industrial zone with 23 nodes, and the city center with 28 nodes. On this picture we can see the location of the municipality of LOG-a-TEC, and on this picture we can see the sensor nodes mounted on light poles. This is how the actual testbed looks like, with all the nodes pointed on map, and with we can see in which band they operate and their ID, which is used to reach the nodes through our infrastructure. And this is the industrial zone cluster, and before this is the city center cluster. On this picture we can see the location of the local DVB-T transmitter, and we will also use we will sense this transmitter in one of the demos later on. This slide presents how the LOG-a-TEC Vesna application is developed. So at the bottom is STM32 firmware library. Then we on top we feed the Vesna drivers, and then we have directly the application without operating system, and we have a REST interface for remote access to the nodes. So here on this slide we can see the complexity from through common data format, we have the REST interface on the sensor nodes, and then we have the C API and then the register level access to the firmware in the firmware. The REST interface uses a 16-bit network address. The nodes act as servers on the network. They expose various resources, and the resources are addressed by name. For example, sensing slash device status. Each resource can have a get or end post method, and we will also see how this works. So get method is used for getting something from the node, and post to uh, to post something to the node. Uh, and the experimenter's computer acts as a client, which sends requests to nodes and receive responses. And the system can only handle one request at a time, because the sensor nodes are capable of handling only one request at a time. So on this picture we see the complete infrastructure from the user. So the user will make a request. The request will go through the internet to the HTTP server, which will translate the HTTP request to the Vesna Vesna lightweight client server protocol request, and this request will reach the Vesna coordinator, and the Vesna coordinator will know to which node to forward this request, and then when the node gets the request, it will make a response through the same path back. This is our simple web management interface, and here we can see how simple is to send get and post requests directly to the node. In our demos we will use the Python library abstraction over the whole protocol. So in this way we even simplify the development of the applications. So now we can start with the installation of the Python libraries. I will go to the terminal, and I will execute these commands, and later on we will start the demos. Okay, so first we start with the exporting the library path. So this is where the libraries will be installed. Okay, then we need to download the libraries from GitHub, but I already done this step, so I will go directly to the installation. Okay, I will just copy paste the comments. Okay, here we can install the libraries. Okay, and we also need to install the spectrum sensor Python library. Okay, is a spectrum sensor. We need to go to the Python because this is also the C application. Okay. And now we will start with the demos. The first demo is a very simple one. we will only request a hello. We will only send a hello request to the coordinator and get and receive its response. So let's start with the first demo. Okay, we send the hello message to the coordinator and we received its response. So if we look at the presentation, we are the user, we send the comment through the internet to the HTTP server, and then the application on the server sends a request to the Vesna coordinator, and the coordinator sends back the response. The next demo is sending a request to the end node. So the request will go through the coordinator will read the ID and forward the request to the node, and the node will respond back with the microcontroller temperature. Okay, let's start the second demo. Okay, here we see we got the response. We send the get request to the node 21 for the microcontroller temperature, and we got back the not calibrated temperature of the microcontroller. Let's go on to the third demo. The third demo is a demo of the spectrum sensing interface. This Through the spectrum sensing interface we can configure the frequency range, the channel number, and settle time required after the channel change, and also the channel bandwidth. So this is the third demo. Okay, so we send the request for configuration to node 36, which is CC1101 radio, and we got back the feature set it has, and then we send the request to node 45, which has a CC2500 chip. This is a 2.4 gigahertz radio, and at the end we send to the node 21 the request for sensing configurations, and this is the UHF receiver. Okay, this is just for information. And then we go to the fourth demo. Here we see the spectrum sensing interface of the Python library. It has several classes, and the first one is the spectrum sensor. This is a wrapper around our custom protocol for communication with the sensor nodes. Then we have the config list. This describes the possible hardware device configurations, which we just saw. And then we have the sweep config, describes frequency sweep and hardware configuration like start, stop, and step frequency. And at the end we have the sweep. This is basically the result of the spectrum sensing, and it's a CSV format of the timestamp, frequency, and power. So if we start the fourth demo now. Okay, so what we can see here is basically a continuous sending commands for a single spectrum sensing sweep to the UHF receiver, and on the diagram we can see the plotted measurement, plotted power of the DVB-T transmitter in LOG-a-TEC. Okay, we can close this now and go on to the fifth demonstration. The fifth demonstration is a signal generation interface. Here we can set the usable frequency, the power range, the channel number, and transmitted waveform. And here on this slide we can see the Python library classes which are used for signal generation. The first one is again the wrapper around our custom protocol, and then we have the config list describing the hardware device configurations, and then we have transmitter config describing the signal transmission, the hardware configuration like frequency and power, and then we have the signal generator program for transmission configuration, start, stop, and duration. Okay, let's start this demo. So what we see here was a very short generated signal just to see if it works, and the next demo will combine all the features described in a pre-programmed application. This is also our last demo, and here we will use again the spectrum sensing interface, but we will use the storage of the spectrum sensing on SD card. So we will send the task to the node, we will check if the task is complete, and then we will retrieve the results from the SD card. So this demo is a little longer because what happens, we programmed one node as a transmitter and the other node as a spectrum sensor, and now the one of the nodes started transmitting and the other is sensing, and the sensing node is storing data on the SD card, and when the demo will be finished we will download the data from the sensor node's SD card and store it in a text file, and then we will plot these measurements on graph, and at the end we will also check in the Python code to see if the graph and the code make sense. So now we have to wait a little bit for the downloading of the measurements from the node is finished. Since Zigbee network is quite slow, it takes a while, but hopefully it will be finished soon. Okay, I guess it finished. So what we want to do now is to plot these measurements which were downloaded in the text file, CSV file. Um, okay, so in the left diagram we can see the transmission going on the 2.425 gigahertz, and now we can check the Python code if this is what we configured the transmitter. Uh, we can go directly to the line where we configured the transmitter, and this is this line, and we can see that we configure it to transmit on the 2.425 gigahertz. Okay, this is all from us, and if you have any questions, we will be glad to answer them.